All right. Good evening, everyone. Once again, it's glad to be here once more. So we are wrapping up with the entire thing, and I'm really excited for how far we've come. All right. So we're going to be having our last class next week, Saturday. So because I plan on having a class within the week, and then our last class will be on Saturday, because I just want Sunday to be not the usual class where I come and teach. So we'll have to do something different. So it's not going to be the regular stuff. Anyways, but let's just focus on what we have at the moment. All right. So yeah, today we're going to be looking at two things. We're going to be looking at hyperparameter tuning and overfitting. Okay. Give me a second, please. Okay, so we're going to be looking at overfitting and hyperparameter tuning, and we'll try to just cover the whole thing in this particular class, because next week we're going to or this week rather, we're going to be wrapping up with some other stuff that you might need to know, or you need to know actually. All right, so let's see. All right. I'm just going through the group messages to see what we have. Okay. All right. So we're going to get back to the other stuff, but let's just try to finish up with what we have for today. Hey, Woma, I saw your message. I really hope you're okay. I'm going to reach out to you after this class. Just hope you're fine. Anyways, so let's look at overfitting and hyperparameter tuning. So yesterday we discussed ensemble learning, right? We looked at different algorithms. We looked at ensemble techniques, bagging, boosting, and a whole lot of other stuff, random forest, and what have you, right? So today we're not going to be looking at the algorithm itself. We are going to be looking at some techniques and some other concepts in machine learning. All right. So today we'll start with overfitting and underfitting. So previously we've been talking about overfitting, and all of that. Most of us were just probably confused on what it actually means. Some of us went on to research and tried to see if they can get some info on it, which is a good practice. While some of us have been waiting for us to talk about it in class, whatever works for you. So the video for yesterday's class is available. So please, if you have not gone through it, and if you need to go through it, please do so. All right. So what exactly is overfitting? Someone asked a question yesterday, which made me say some few things about overfitting. So we're just going to elaborate on it today and just spend more time talking about it. So now overfitting is basically when your model learns too much from your data. All right. So when let me just try to take it from the bottom. Let me break it down. So the essence of training a model is to kind of to capture a representation of the real world, right? So we do that by exposing the machine or the computer to data. So the data you are getting, right, is a representation. Is actually a sample of the real world. So that's what we are using to kind of represent the actual or the entire category for the entire category basically that we are like working on, right? So let's say we are working on let's say spam detection model. So we get like 10,000 spam data sets. So those 10,000 spam data sets, it's actually a sample, right? Because the real number of spam data sets, it cannot be captured actually, right? For you to use the exact population of spam data set, you have to go through every single spam and non-spam data and like compile them together and then use the data. So it's impossible and infeasible to use the exact. So in statistics, there's what we call population and there's what we call sample. All right. So population is the exact target of interest, right? The study of interest, what you're actually like working on, right? So why the sample is a representation of your population. So most times when we are working with data in data science data, now what we are actually working with sample, right? It's very impractical or unfeasible to get the exact population. So when you use a sample in whatever thing you're doing, obviously and apparently there will be a bias, right? There will be like a discrepancy because you are not using the exact number of, or you are not capturing every single uniqueness or every single thing in that population. So that bias is what we are going to try to minimize basically, right? So in when we come to overfitting is when you allow your model to learn too much about that data, that sample that you are exposing it to, and you don't want it to be that way because what you want to do is just to allow the your system or the computer have a general knowledge, a general idea of the data and the relationship that exists between the data, so they can generalize, right? So there's another word, another like terminology in machine learning that we call generalization. So we want our model to be able to generalize well to unseen data. So when they see a new data, they would actually use the knowledge they have that came from the training data set basically to like make a proper prediction, a close to accurate prediction, right? But if what the model learned from the training was too specific to the training data, it will be difficult generalizing because if it did not see the exact same thing that is present in the training data, it's going to be confused and will probably give you wrong predictions and all of that. So that is basically what overfitting. Overfitting is learning too much detail. So it's just, let me give an example now. So in a case where let me use the same example I used when I introduced machine learning. In a case where you are training your daughter to identify cats, was it dog or cat size? I don't know. So let's just say identify dogs, right? So you are training your child to identify dog when they see one. So let's assume that, there are actually there are varieties of dog species. Like you don't just see a particular dog and assume that every other dog is the same, right? So let's assume that you are seeing a lot of dog species, but then the ones that you exposed or you showed your daughter, they were just like a select few species, and when you were describing the features to her so that will help her know that this is a dog, you were being so specific, right? We are going into like species details, like telling you that, okay, this particular that if you see a dog that has, if you see any object that has dot 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 or anything whatsoever, that is a dog. So she begins to learn unnecessary details, too much details about a dog, that when she now sees a dog, like let's say in case where she's not learning and she just wants to like apply the knowledge that she has got, she now wants to like identify that object, and she didn't see those specific details she saw during training, like she didn't see spotted spot on that dog on body. She might conclude that, okay, this is not a dog, right? Because she learned too much details during training. The aim there is to actually understand a general to get a general overview, right, of dog features that can translate to other species, because you are not just using only one example. So there are varieties of uniqueness when it comes to different samples. So the same thing applies in machine learning. When you are training your model on a data, you want to ensure that it does not learn too much. It does not learn too much unique and unnecessary information from the training data set. So you want to minimize that level of understanding so that it can generalize well. All right. So yeah, that's basically it. So let's just start with overfitting. So overfitting occurs when a model learns the details and noise in the training data to the extent that it negatively impacts the performance on a new data. Right, so that is basically the same thing I'm explaining. So when it learns too much on a training data, it begins to learn noise. Noise are like unuseful information. So obviously there's some information that are not necessarily useful. So it begins to learn those things as well, right? So it's just like you trying to read for an exam. Okay, so you are trying to read for an exam, and you are given a textbook, and that textbook is your training data set, and the exam questions will be the test data set, which you are going to have to make predictions on that you don't have the answer to. So instead of you learning the like in general concept in the textbook, you begin to go even extra mile to read the footnotes, to read references, to read introduction, to read things that doesn't really matter. So you are basically overfitting under your textbook. You are learning too much than necessary. All right. So you're supposed to keep the learning at a point where you are getting the necessary information that can be translated when you see questions, right? So it's not when you see, because the questions you'll be getting will basically be questions on the core aspect of the topic that you're learning, not all those noise and everything that you're reading. So you don't want to overfit on the textbook, and it's the same thing that is happening here. We don't want to overfit on a data, right? So some models tend to overfit a lot, even without like you doing anything. They just tend to overfit, and we're going to look at the reasons why they overfit. So remember yesterday's class, we look at some model, and we some of the disadvantages of some of those model algorithms were like they actually can overfit. There's a possibility that they overfit, they learn too much, which if anyone can remember, can you just tell us which of the algorithms we looked at yesterday has that tendency of overfitting? I need more responses. Just one person. All right, because of time, who is in Bagging and Bootstrap? Bagging and Bootstrap are not necessarily algorithms. They are just techniques, right, that algorithms borrow. So bagging and boosting, they are not algorithms exactly. They are just techniques that are used. So
So basically, like out of the models that we looked at, decision tree generally, they are known to overfit on data. All right, they are very, very, very prone to overfitting. Very, very prone to overfitting. So it's something that you need to take note of. So it's something you want to avoid. When building a model, you should take note of overfitting. And I'm going to show you how to identify a model that is overfitting, right? So that you can avoid it, right? So let's just proceed. So basically, overfitting would mean that the model performs well on the training data, but poorly on testing data sets. Okay. So if your model is overfitting, that means it has learned too much on the training data, but poorly on the testing. So when you calculate or when you try to get the accuracy or compute a metric on the training data, that particular metric will be higher on the training data and very low on the test data. So you can see here we have symptoms, right? So the symptoms of overfitting on the training data is that the accuracy is usually very high, right? The accuracy is actually usually very high, while on the testing data, the accuracy will be low. This is basically because it knows too much about the training data. So when you ask it any question about your training data, it will almost always get it. So it will have high accuracy. But if you take it away outside of this training data and you show it a data that it was not trained on, it's going to perform poorly, all right? So that's basically how you know, because you're going to get low accuracy on testing data sets, right? So these are the symptoms. This is how you actually identify overfitting. So when you compute the accuracy on training data sets is going to be high, and then the accuracy on testing data set is going to be low. So once you have that discrepancy, you are going to you definitely know that yes, my model is overfitting, right? So you now try to fix the issue. So what are the causes of overfitting? We have two complex model, insufficient training data, and excessive training time. So these are the three different causes, major causes of overfitting. So when your model is too complex, it can overfit, right? It can actually overfit. So a complex model can be a model that has so many parameters, right? You are like kind of using so many parameters of that model and doing a lot of stuff. Or the model itself, like decision tree rather, it doesn't necessarily have to be about the parameter. It's actually, in that case, is the nature of the algorithm, right? So the way decision tree works makes it prone to learning so much about a particular training set that it's now overfit on the training data. All right. So that's one of the reasons or cause of overfitting. The second one is insufficient training time. All right. Insufficient training data, sorry. So when you have so little training data, it's very easy for your model to overfit because you are showing it just small data sets. So it's going to learn every single thing easily, right? So it is easier for it to learn everything, to see all the data and learn everything because the data is just small, right? So obviously, if you have small data, you are prone to overfitting. So that's why we are always advised to use a lot of data when training model. All right. So when your data set is not sufficient, you are going to be prone to overfitting on the training data. Okay. So the last one here is excessive training time. So when you're sometimes, and these are usually like specific to traditional ML models. All right. So the ones that we've looked at so far. So if you train it for so long, it can also like overfit on the training data. It can make the model overfit on that particular data set. So these are the three most common causes of overfitting. Too complex model that is having so much parameters, insufficient training data, that is your data set is small, right? And excessive training time. So you just take note of those three causes. So what are the solutions? How do you handle overfitting? So the first thing here, obviously, is to simplify the model. So you can start by just removing parameters and simplifying your model basically by not having so much hyperparameters. All right. You can also collect more training data. So if your data set is small and is overfitting, the obvious thing to do is to add more training data, right? So add more training data sets. So it's just like this insufficient training data, right? It's just like having a big textbook of like 1,000 pages and then a very small textbook of like 20 pages. If you are told to learn the information in two of them, right? Obviously, you're supposed to cover everything from front to back. So the approach you will use when reading the 1,000 pages, that you try to understand the key idea in each page. So you don't go over all the details, all the words in this page. You just flip over it, try to understand the key idea. Do that for the 1,000 pages. All right. So when you are done with that book, you kind of have an idea, a very good generalized general idea in that particular textbook, right? But for the 20-page book, when you are using it to prepare for maybe whatever it is, you are going to obviously have enough time to go over everything, to the point that you might even go over too much details. Like you might finish it like before time and still go back again and start reading unnecessary information and all of that. So that's what happens when you have small data sets. All right. So that's what happens when you have small data sets. It allows your model to learn all the details of your data set easily, and it's basically just overfit on that data. Someone is asking, is it right to say that overfitting can also occur via training a model with dirty data set? No, it's dirty data sets would have nothing to do with overfitting. If you train your data with a dirty data set, basically the output basically would not make sense, right? The performance will be poor generally, right? It will not even give you a good accuracy on the training data set. All right. Thank you. I think that's the word that fits it. Off-fitting. It's just off. Like it's not performing well. It's just there. The performance will be very bad because it's not understanding any pattern, right? So what you're trying to do in training is to understand patterns. So if your data is dirty, the pattern is not very clear, right? So it would just mess up the whole thing. So it's just like having that particular textbook, and in that textbook, the arrangement of the text or the topics and subtopics and everything is scattered. So you that are reading it, you don't even understand what you are reading. You are just trying to make meaning out of what you are saying. So once you have finished reading the book and then you are given a question based on that book, would you be able to answer it? No, right? You because you didn't get any knowledge, any meaningful knowledge from the book, because the book was, let's use the word dirty. The data or the information in the book was dirty, right? So you always have to clean your data before anything. So that, I think that just answers that. So the third solution to overfitting is using regularization techniques. So there are techniques we call regularization. We are going to look at them that should be either the last class or the second to the last class. So we have 2 more classes, right? So we'll look at regularization techniques, which helps in handling overfitting. And we can also employ cross-validation to monitor model performance. So there's a technique called cross-validation. We're going to look at that in today's class as well. So that's for overfitting. I believe this is a decent explanation, right? There is really nothing like difficult about like overfitting. It's just when your model learns too much details, unnecessary information, that it doesn't now perform well on same data. So this example that you're seeing is an example of overfitting. So this is supposed to be a linear regression task, right? So what you're supposed to have here is a straight line that kind of best fits the data. So in this case now, you are literally there are actually adaptations of linear regression, which are called polynomial regressions, right? So these are cases where you want to
the relationship is not exactly linear, so a straight line will not do justice to it. So you can just add polynomials to kind of bend the lines and all of that. So in this case, this can be polynomial regression when you overfit, like learn too much, right? You can see that the regression line is touching every single data point, which is not supposed to be so. So when you calculate the error, in this case, what are you likely to get for the error in this particular model that we have here? So based on what you're seeing, what do you think the error might be? Today is actually just dull. I don't know why. We're correct. So the error is going to be 0 because the prediction would be exactly the same thing as what the original value. In a sense, you might be thinking, yes, it's a good thing now. It's actually a good thing because if you calculate the accuracy for your training data set, you're going to see 100% accuracy. But that is not, that accuracy doesn't really matter because what you're trying to use your model for is on unseen data set, the ones that you didn't see. So when you now take that model to another data set that has not been trained on, you are not going to be seeing very, very poor performance, right? You're probably seeing accuracy score of like 50, 60, like let's say highest Hyperparameter you see 70. So you can see that you're not asking yourself a question, why is that my accuracy on my training data set was high at like 100%, and then while using it, it's not performing poorly. So that's just what overfitting is. Like at that point, you should know that, oh, your model is overfitting. It overfitted on the training data set. So you now start to fix the issue by using either of the solution that I mentioned there. So you should be able to know what caused the overfitting. If your data set was too small, then you add more. If you use the complex model with so much parameters, you can try reducing the parameters and all of that. And you can also try regularization techniques. So regularization techniques are like one of the best options to use to help fix overfitting issues, right? And most of these models, they actually have regularization parameters embedded in them, okay? So you're going to see them. So it's an option as well. So from there, you can know which exact solution to use. So that's it for overfitting. Now let's look at underfitting. So underfitting is like the opposite of overfitting. Underfitting is when your model is too simple. Underfitting occurs when the model is too simple to capture the underlying patterns in the data. Remember that the essence of creating a model is so you can understand patterns and relationships, right? So for overfitting, you are understanding too much to the point that you are getting to learn unnecessary info. All right, that's for overfitting. Why underfitting is when the model doesn't even learn enough. It doesn't learn enough for you to have a good model. So it's just like you trying to prepare for an exam, and then you have just like a day to the exam, and you've not read anything at all. So you now have a textbook that you're supposed to use for the exam, and the textbook is about 2,000 pages. So within one day, you just try to just flip over the book fast, like try to just see every single thing at a glance. So you are literally like seeing what is there, but you are not capturing the idea, you are not understanding it. So when you finish with the textbook, when you finish flipping the textbook, you probably realize that you really don't know much, right? So when you get to the exam hall and you see questions, you'll be wondering, where is this question coming from? Like, you don't understand, you don't know how to answer. So it's the same thing as underfitting. Your model doesn't really capture the patterns in the data well enough, right? So when it now sees new data set,
it doesn't know how to make prediction. It doesn't know the right predictions to make. So for underfitting, you're going to have low accuracy in your training data set and low accuracy in your testing data set. You discover new topic for exam. Exactly. But I say you get experience. Right. So that's the symptom for underfitting. You're going to have low accuracy on both training and testing data, basically. All right. So when you see this, you know that your model is overfitting already on your training data set. So what are the causes? Your model is too simple, right? And you have insufficient training time. Okay. So another reason might be having too much data. So let's say you have although there is a trick, there is a nuance to it. If you have, let's say, 100,000 data sets, right, and you're using a model that is not really complex, right, to capture patterns from that, and you have a lot of features, right? If you have a lot of features and you have a lot of samples, you can be prone to underfitting, if you don't give your model sufficient time to learn or to train on that data set, and if you have too few parameters, all right, so these are the things that might cause underfitting. So generally, okay, let's just go to the solution. So the solution to this is to increase model complexity, train for longer period, and use more relevant features. So you can see the key here is what? Use more relevant features. So we're going to look at feature selection, how to select relevant features in like in one of our last classes, right? So these are the things to do when you like encounter underfitting. So generally, you should try as much as you can to avoid these two things: overfitting and underfitting. All right, these are concepts that are very important to know in ML, right? So you should try to avoid both ends, avoiding your model to underfit on your training data set and avoid it to overfit on your training data set as well. So now you know the reasons why they can overfit and the reasons why they can underfit and what you can do to fit them. So now this is just an illustration to show you exactly what a potentially underfitted model is. So this is a straight line, right? This is a linear regression. But in natural sense, this regression line might not be fitting well on this model. So ideally, what you should probably do in this case is try to let's say you can add polynomials, right? Like add some just do some tweaks and all of that to make this straight line a little bit, like you can bring it up. Anyways, this regression line, first of all, is not even the best regression line. The regression line should be somewhere in the middle here, right? So you can even try, like, I'm still training your data to get a better fit, right? But if at the same time it's simple, a regression line like your linear regression isn't giving you a very good performance, it's underfitting, then you can now try other models like polynomial regression, where you add polynomials. So what polynomials does is that it tries to bend this line a little, so it deviates a little from being straight, so you can curve a little to fit the data better. But anyway, of our curriculum. So, but that's it for underfitting and overfitting. So now we're going to look at another like very close concepts. So they're almost the same thing, right? So and they are bias and variance. So bias and variance are another two concepts in machine learning that you try to avoid. So you basically, I hope everyone is still following. Like, I don't know why it is unusually dull. I hope everyone is still following and can hear me clearly. All right. All right. Okay, great. That's more like it. So we're going to also look at bias and variance. So bias refers to error. So bias obviously is like a deviation from what is true. Okay. So just look at bias as an error. Like for now, right? So when you think of bias, right, you think of error. So definitely you would always have bias in your ML model. All right. So I'm tempted to ask why is it so? You would always have bias. Yeah, let me just ask it. It's not like I've said anything about bias yet, but why do you think we would always have bias, regardless of how good our model is? Why do you think there will always be bias whenever we have a model, no matter how good that model seems to be? So let me just give you a hint. It was what I said at the beginning of this class, like the explanation I made, right? So let me just see if anyone can just put two and two together and figure it out. Okay, probably based on some assumption made in the model. In case we don't have enough knowledge of the person in question, there will be bias. No data is ever perfect, okay? Because our model cannot be perfect. Just like testing a software, no matter how you test, it always be bug. Okay, clerical error. The data used in building the model is not exactly the same. The same as what exactly? You're actually like most hitting it on the head, but the same as what? Bias is relative to the data, cause not the 100% of the data set is trained on reality. All right. Some of you are actually like close to the answer, right? So you think you have an idea. But basically, why we would always have bias is that we are not training our model on all the data that we usually train it on. All right. Remember I told you about population and sample. That the population in statistics, population is actually the entire possible data that corresponds to a particular topic of interest or a particular area of interest. All right. So I use the spam detection model as an example. Like if you want to create a spam model, right, we can't possibly use all the entire example or instances. So we have to like just get a data set that represents what we think spam and not spam is. So that's what we call sample. So that discrepancy between the real data and our data set we always have or we always introduce bias because there is we are not getting the exact same thing, right? Like we're not getting the exact same data that the entire data basically we're not getting the entire data possible. So we use a sample, and if we are having sample, then we are going to obviously have a bias. So what we try to do in ML is to reduce that bias as much as we can. So bias can lead to a high bias. So there's something you need to take note of, that high bias can lead to underfitting, and for variance, high variance can lead to overfitting. So I'm going to just open a note, because there's a combination that every data scientist needs to know, right? So that you know exactly when the model is good enough. So what you're trying to avoid is that you're trying to avoid high bias and high variance. You're not trying to avoid bias. It's not possible to avoid bias. And it's not also possible to avoid variance. So I'll talk about what variance is, but let's just look at this. So we have what we call high bias. We have bias normally, right? We can have, our bias can be high, ours can be low. So we are always aiming at a low bias. So we have high bias, we have low bias, we have high variance, and we have low variance. All right, so what we are always aiming at whenever we are creating any model is to have low bias and low variance. So this is a good model. All right, this is a good model. So we don't want this is a good model, right? We don't want this high bias and high variance. This is bad, like this is bad model. All right, this is a bad model. We don't want this at all. All right. So we don't want this. We also don't want high bias and low variance. We also will try to avoid this. All right. You can say not so good model. All right. We can also have something like low bias and high variance. So whatever model we build, we would always we would have either any of these combination. Like definitely, you would always have any of this. So there are ways to assess it to know which particular place your model falls into. Let's just look at them. So this is how we actually look at bias and variance. I've not explained them yet, but just keep this one at the back of your mind first. So now let's go back to our material here. So bias refers to the error introduced by approximating a real-world problem, which may be complex by a model. So this is basically what I was explaining, right? So you're trying to approximate something, right, that is there in reality, right? I'm trying to approximate it to a model by using a data set or a sample that represents that problem. So you don't always get a perfect representation, right? So the perfect representation is not always possible. So high bias here is when the error or the so in the case of training data set and testing data set, when you have low accuracy on your testing data set, and then you also have low accuracy on your training data set, you have what we call high bias, right? So for instance, now let's say you have something like this. So you have your train data, and you have your test data. So I'm going to show you, this is for bias. High bias, this is going to be for high bias.
And then this is going to be for high variance. No, this is not a code, man. So these are train data and test data. Okay, so let's assume you built your model now, and you have on your train data you have, let's say, 60% accuracy, and then in your test data you have, let's say, 55%. This is a problem of high bias, right? And this is also the same thing as underfitting. So when you have high bias, you are obviously most of the time you are underfitting on your training data set. So you can see the difference between these two. Your training data is 60%, while your test data is about 55%. So the difference in accuracy is 5%. So this particular model now has what we call high bias and what? Low variance. All right. So the variance is just the difference between the training data set performance and the test data set performance. So in this case, you have high bias and low variance. Right? You can see it here. So I told you that whenever you have your model created, your model will always have any of these case, right? Any of these will fall into any of this category here. Right? So in this category here, our model has what we call high bias and low variance. So which is bad already, right? You don't want your model to be in this category. So let's just use another one. Let's see another example. So in this case, we're going to demonstrate high variance. So let's say our model is let's say 95% here, test data set, and our model is the test data set is let's say 60%. So this is a case of high variance, right? The difference between the training data set is quite high. So this is I think 35, right? 35% difference, which is high. So that represents your variance. So your variance in this case is high, while your bias in this case is low. All right. So you have high bias and low variance. High bias and low variance. Right. So this is in this case 95% is actually low bias, right? You use your train data set to check it. So let's give another example. And in this one, you're going to tell me what the bias and variance is. So let's say we have train data. I'm just using accuracy at this point. It might be any metric you are using, right? It doesn't necessarily have to be just accuracy. So I'm just using accuracy. It's just illustrative. Let's just say we have something like this. So we have. So someone is asking on the group, at what percentage can we call overfitting and underfitting? This is actually another question that will most likely pop up in your mind. Like, it's a practical question, basically. But there is no particular hard-coded value where you say your model is overfitting at this point or underfitting. But they are just like let's say strong signs to see, right? Your accuracy, if your accuracy is on your trained data set is high, let's just put it from 80% and above, right? You're probably 80% to 90%. Might not necessarily be overfitting, right? Let's say from 90% and above can be considered overfitting. So overfitting on your trained data set is when it is actually very, very high. Let's say from 90% and above, 95% sometimes, you start from 95% basically. So around that range, but there are other things to look for. So you look at your test data set as well.
So if your test data set is high as well, if your training data set is 95% and your test data set is, let's say, 85% or 90%, would you consider that overfitting or not? I want us to answer this one. If your test training data set is 95% and your test data set is 85%, will you consider it overfitting or not? All right, I need more responses. Please, just want to ask and to know exactly how we are thinking about this. Okay, so we're actually like on board. We're actually on board, right? So it is actually not overfitting because your test data set accuracy performance or performance is closer to the training accuracy, which basically means that your model is generalizing well to unseen data. So it is not overfitting. So for you to judge if something is overfitting, you use both your training data set or test data set. In some cases, they usually use validation data set, but just for the sake of this program, you use your training data set performance, judge it with the test data set, training out test data set performance to know if it's overfitting or underfitting. So a very good rule of thumb to follow is if the gap between your training and your test is 5 to 10%, then it's probably okay. Like it's okay. But if it is greater than 15 to 20%, then there is overfitting, right? Especially when your training data set is high. All right. So yeah, that's basically it. Let's move on to let's continue with bias and variance. So in this case, our training data set is 70%, while our test data set is 50%. So is which level of bias and which level of variance does this model have? Is our variance high or low? And is our bias high or low for this one that we have here now? Okay, someone said, okay, Kingsley, high variance and high bias. Nigeria, high bias, high variance. Also the fitting. Iwoma, both are high. Felix, high bias, high variance. Abdulhamid, both are low. Justice, yes, very high. Okay, someone said high bias and variance. So now seeing this, like you should know that the bias in this case is actually high. All right. So our bias here is high bias, and our variance here is looking at the difference between these two. You know that the gap is actually too much, right? 70 and 50. So the bias, this is like the worst position to be in for a model to be in, having high bias. Like it is not even performing well on the training data set, and coming to the test data set is even performing much more worse, like way off. So that is a very, very bad place to be in. All right. So let's just take another example and then we move on to the next step here. So we have another one, train data, and we have
data. Let's say in this case we have let's see. All right, let's say we have models to perform like this on, let's say 95%, and then we come here and it is 80%. So what do you consider this model to be? Like what category do you consider this model to be in? All right, I'm saying low bias, low variance, both slow, good model, high variance, low bias, low bias, low variance, low bias, low variance. So I feel generally everybody's saying some said high. I don't think so. So this particular model is a good model actually. Like this is low bias and low variance. So this is a good model, all right? Good model. So let's just go back to the first one. So this first model, is it overfitting or underfitting? Is this model overfit? Is it overfit or did it underfit? This one highlighted here, is it overfitting or underfitting? Yeah, it is underfitting, all right? So it is not learning well, like in the training data set, and then the performance is also like low. So this next one here, is it overfitting or underfitting? The second one. Exactly. It is overfitting, all right? So you can see that the training data has a very high accuracy, and then we come to the test data, to unseen data, you can see it is performing poorly. That means it has overfitted on the training data set. All right. So that's basically that for that. So this next one that we have here, is it overfitting or underfitting? Exactly, it is underfitting. All right. So I think with this example, you should be able to like understand or identify when your model is overfitting or underfitting, or when your model is when your model has high bias and high variance. I feel explaining this concept like is better this way, right? Because like just talking and talking and talking might not get you to understanding. So this is the best approach to understanding. So I believe you should like just helps me knowledge on all of that. All right. So for bias, we've explained it already. So these are like the different characteristics. So an example of bias is when you're using linear regression on a non-linear problem, right? You're going to have a bad accuracy on the training data. So for variance, the same thing. So everything I explained, they are just like represented here. So I highlighted it basically. So the variance refers to the error introduced by the model's sensitivity to small fluctuations in the training data, right? So high variance can lead to overfit. Okay, so especially when you have the accuracy of the um, training data set to be high, then high variance might be to overfitting. So I want free time, just like study those examples once again and try to understand it, because it might actually like try to put you on board. It's just very straightforward. All right, so let's move on. So there's what we call a bias variance trade-off. So what you're trying to do is that you would always have bias and you always have variance in your any model you're creating. So you are try as much as you can to reduce both of them to have an approximately low bias and low variance. All right. So this is a key challenge in machine learning, basically. So a model with low bias might have high variance and vice versa. So that is what we just illustrated now. So you just want to ensure that you are in a better position, like you are in the middle ground. You're not like on the high side and all of that. Your model is like approximating towards low for bias and low for variance. So the goal is to find the right balance where both bias and variance are minimized to achieve the best generalization performance on our data. So your aim basically is to make sure that your model can generalize very well, like it can approximate its knowledge on unseen data, right? So because the reason why you're creating a model is to make predictions on unseen data. So when when your predictions are not really like correct, then your model has a problem. So that's when you start to investigate and all that. You can see that there are a lot of knobs to turn, a lot of like things to check in model building. So it is not just like straightforward like that. You have to actually like just do some investigation and make sure that your model is good. Okay, so that is it for that. Let's move on to the next thing we have today, which is hyperparameter tuning. So hyperparameter tuning is attendance is on already. So you can go ahead and I think the assistant course rep mentioned that. So you can go ahead and sign your attendance. So let's look at hyperparameter tuning. So this is hyperparameter tuning, is a process of optimizing the hyperparameters of a machine learning model to improve its performance. So everything that you are doing at this point is to improve the performance of your model. All right. So that is the aim of all these things we have been talking about. Even the classes that we're going to look at going forward, they are mostly going to be centered on improving your model performance. All right. So because you want to have your model with a very good performance, especially when it's something that people would be using out there. So hyperparameter tuning is the process of optimizing hyperparameters of a machine learning model to improve its performance. Hyperparameters are parameters that are not learned from the data, but set. Let me just highlight it. Hyperparameters are parameters that are not learned from the data, but set before the learning process begins. So I've explained this already in previous classes that parameters that we can change or tune when creating our model, they are called hyperparameters, right? So we have what we call parameters. Parameters are the things that are learned during training. So you don't really see them, but the weights are stored in computer memory. So that's the model, right? What makes up a model are weights. Weights, they can call it weights, you can call them parameters, anyone. So what makes up a model are weights. So when you hear things like OpenAI has released a model with 17 billion parameters, what it's just trying to tell you is that parameter is just like the size, its knowledge size. So that parameters are the things that it learned during training. So most of the time, the higher the number of parameters, the better the model, right? Especially for all this large-scale AI model that they are creating nowadays. So those are parameters. They are learned during the training process. That is basically what the model is trying to even learn. That is what takes time, right? So, but hyperparameters, they there are parameters. Now, we are saying a lot of parameters. I need you to just separate them. So these hyperparameters, they are parameters that are not learned. They are set before the training process begins. So those are the parameters you can actually tweak. You can tune them. You can change them to influence the performance of your model. All right. So I think we all understand this at this point because I've mentioned it several times. So example of hyperparameters are learning rate, number of trees in the forest. So all the things I showed us yesterday, those are hyperparameters, right? So the hyperparameter tuning that we are seeing here is an approach to tweak hyperparameters so that we can get the best model, all right? So there are two approaches to tuning hyperparameters in ML, right? The first one is manual search. Second one is what? Automated search. So manual search is very time consuming. Like nobody uses manual search. We're just saying it here so we can distinguish it and contrast it with automated searches and know how much better the new method for tuning a hyperparameter is. So for manual search, what you most likely do is that you're going to manually select and test different hyperparameters. So when you want to test hyperparameter, what you do is that you have to train several models with different hyperparameter values. All right. Let's say you want to train a logistic regression model. You train model 1 with a different hyperparameter, train model 2 with a different hyperparameter, train model. So let's say you want to change a combination of 10 hyperparameters. You have to train 10 different models. So if you're doing it manually, you're going to have to do it the manual way that we've always been doing. So you train them one by one and one at. So you're literally training 10 models. So it's time consuming and it's really not efficient. So that's a manual method, and that's not what we are going to be doing, right? So the second method here is automated search, right? So automated search is a more efficient way of doing hyperparameter tuning. So you will have tools in SQL that helps us do that, right? So the two of those methods, right? The tools that we have, there are two different types. So we have GridSearch and RandomizedSearch. So these are the two techniques for hyperparameter tuning. Remember in your project, the hyperparameter tuning itself has a score, right? So if you don't do hyperparameter tuning in your project, also you are losing, I think, about 5 marks or 10 marks. I can't remember. But also you're going to lose marks because I want you to test out different hyperparameters, right? So you should implement either of these in your project. I'm just giving you a bonus at this point because most of you might not see it. So these are the ways or the techniques to tune hyperparameters. Let's move on and finish up what we have to do. Before we go into GridSearch and randomized search, I'd like to explain a concept that is being used in these hyperparameter techniques, which is called cross-validation. So this cross-validation even makes your the model outputs to be better. All right. So what cross-validation means is it's a technique that is used to evaluate the model's performance and ensure it is able to generalize to independent data sets. So the key stuff in cross-validation is partitioning of data set into subsets. All right. So cross-validation, when you talk about cross-validation, just imagine you bringing out your data sets. Now, let's say you have 100 instances or 100 sample. Your sample size is 100, and that's what you want to train your model on. So if you're going to use cross-validation, what you do is that you split, right? You split the data set into K subsets. So we call it K. So what we actually call this, the technique, the actual name for cross-validation in SQL is K-fold validation. So you separate your data set into K-folds. K-folds, K refers to the number of splits you want to make. So the same thing as KNN, K there is number of neighbors. So whenever you hear K, most of the time it's just like a placeholder that will represent the number of whatever it is you want to do, right?
So K here the K in cross-validation is the number of folds or number of subsets that you want to create. So let's say you want to use K equal to 3, right? So what will happen is that you're going to have 3. You divide your 100 samples into 3 different parts. Okay, so all the things that I'm saying, you're not the one that will do it. It is going to happen. Like in GridSearch, this is what happens basically. It uses cross validation. So the data set, let me scroll down. There's a hand. You can see it here. So this diagram illustrates what we mean, what cross validation does basically. So let's say we have, okay, let's use 5 folds. So we have 5 K-fold cross validation basically. We have 5, 1, 2, 3, 4, 5. So this is our data set. Our data set is in this place is 1,000, right? You can see your data set, so it's 1,000. So what K-fold will do in a case where K equals to 5, it is going to separate we're going to separate our data into 5 parts, right? 5 equal parts. So in this case, separating our data into 1, 2, 3, 4, 5. So each of them will be 200, 200, 200, 200, 200, right? So now, in the first, for the 5 parts, we're going to have 5 different models that we're going to build. So for the first part, you're going to use the first part of your, okay, this is testing. So you're going to use the first part of your split for your test data set, and then you use the remaining for training. All right. So you train a model using this particular split that you have, right? And then you have a particular accuracy score and all of that. So you go to experiment 2, and then use the second part. So the second part here is 200. So we're going to use this 200 as our test data set, and then the remaining 800 as our training data set. So what we're trying to do is that we're trying to show your model the different parts of our data set, so it sees everything completely. Basically, we are trying to expose it to different areas, right? So in our normal model training, we'll just do it once, we'll do test and train split, and then we'll create a model, fine. But in K-fold cross validation, we do it 5 different times or K different times. So if it is just 3, we'll split our model into 3 different parts. Use the first part as our test data set, and the remaining part as our train it, and then get our metric. Do the same thing for the second one, and the same for the third one, and then we'll get 3 models, and then we're just going to like aggregate the models and then get a single output. So this thing is basically like similar to what we said yesterday in ensemble learning, right? But ensemble learning uses cross validation, right? Cross validation, the idea of cross validation, basically. So that, just so you know. So in this case, we have 5, so you can just like follow up with it. You use the first part for the first one, second part for testing, third part, fourth part, fifth part. So you can see the progression of our test data set and our training data set. So you get your metric for each of them, and then compute it and get a single metric. All right, that's basically what cross validation is. So everything that you see here is just a breakdown of how it works. So how does cross validation work? First, we split your data. So the data set is divided into K subset of folds. So you can call it a subset of folds. So a common choice for K is 5 or 10. So which basically means that you have 5-fold or 10-fold cross validation. So then you train and validate. So the model is now trained K times. So depending on the number of K you have, you're going to have that K number of models. So and then you're going to like use a subset of the data set for training, and then remaining for validation. So validation here is same thing as testing, all right? So you can call it validation or testing. So just to simplify things basically, right? So that's what we mean by validation. So you do that the K number of times and all of that. So you see here, 1 fold is used as validation set or testing set, all right? And then the remaining fold are used as training set. So you're going to now train on the training and evaluate on the testing set of validation set. and then the performance metric is now recorded. So you do the same thing for the K number of folds, right? So that means you have different test data set for different folds and different train data set for different folds. So you're exposing your model to different parts of the data, right? So you just get a holistic idea, a holistic training basically. So it's better than just training once. So after that, you now calculate the performance. So after K iterations, you now have K performance metrics, and then the metrics are averaged to give a single estimate of the model performance, providing a more reliable measure of model's ability to generalize. So that's after I've explained all of that. So that's what happened. So the obvious benefits of K-fold cross-validation. We have better utilization of data. So you utilize every single data point. So cross-validation allows every data point to be used for both training and testing, right? Ensuring efficient use of the data set. So remember in our normal training, when we split our data into test and train, so the test part, the test data set will never be used as train data set, and the train data set will never be used as test data set. So it just does it once. So but for K-fold, we do that particular we carry out that particular process, but for several parts of the data set, all right? And you have several metrics which you can now combine. So detection of overfitting is another one. So it helps detect overfitting by evaluating the model. So there are a lot of benefits basically for cross-validation. You can actually do cross-validation on your own without, you can do it manually if you want actually. But the reason why we are looking at this is because GridSearch and RandomizedSearch, which are techniques for hyperparameter tuning, uses this technique. So we have model selection, cross-validation help compare and select the best model and blah, blah, blah. So these are just the same things that we have explained. So hyperparameter tuning, it is useful for tuning hyperparameters by providing reliable performance estimate for different hyperparameters configuration. So that's it for cross-validation. Let's just move on to the main thing. So we are looking at GridSearch and RandomizedSearch. All right. We're looking at GridSearch and RandomizedSearch. So GridSearch basically is a systematic approach to hyperparameter tuning. So now I think I'm just going to go over to this diagram here so you can basically see it. So the one on the left hand here is GridSearch, and the one on the right hand here is RandomizedSearch. So whenever we talk about hyperparameter, you think of the parameters of each model. So now let's look at the process. Let me see if I should just go straight to the implementation. Let's see. All right. Let me explain first. Is to give you a problem. And automatically send it computer. Internet what as that your test so remember, we are using cross-validation for each model, right? I told you that GridSearch and RandomizedSearch, I use cross-validation in training. So when you use GridSearch, you are going to actually notice the time it will take to complete, depending on how much hyperparameter you are combining, all right? So the process here is very straightforward. So for GridSearch, it's a systematic approach where a model is evaluated for each combination of hyperparameters in a specific grid. So this is the grid I'm talking about here. So let's say you are working with decision trees, or let's say random forest, or let's use random forest, right? So remember, random forest has n estimators, parameters, and also max depth parameter. Am I correct? If you remember correctly. So it has n estimator parameters, so let's just call it hyperparameter, right? And max depth hyperparameter. Can everyone see me? I think the network was coming up at some point. All right. So as I said, random forest is one of those models that has these two parameters. So the reason why we have it in 2 dimensions is because we're just using 2 parameters. If we have 3 parameters, we would have a 3-dimensional grid, all right? If we have 4 hyperparameters, we have a 4-dimensional grid. So we can actually represent more than 4 dimensions. So whenever we are looking at examples using visualization in machine learning, we're always using 2-dimensional stuff. So in this case, we are combining max depth and n estimator. All right. So let me just show you what we mean by that. So let's use max depth. Let's say we are using max depth, and we are using n estimators. All right. So first of all, you want to check for different values, right? So for max depth, you want to try different depth. You first try, let's say 50, you try 100, you try 150, you try 200. All right. Let's keep this as a list here. So for n estimators, remember what n estimators mean. What does n estimator mean? Can someone remind us? What does n estimators mean? So what does the estimator itself mean? Yeah, it's number of estimators. What does the estimator? Thank you very much, Nigeria. It means number of models, basically weak learners. Right? Since we are using assemble algorithm here, it's going to be a combination of different weak learners, right? Or different base estimator, different base models, right? Or you can call it number of trees required. Abdulhamid, yeah. So yeah, I think we are correct. So we can say, let's start with 20. Let's go from 20 to try 50. We'll now try 100. We'll try 1. So you can just choose any one that you want, basically. All right. So you can choose any number you want. So just try it out. All right. So we have 4 values for max depth here, and we have 4 values for estimators here. So in total, how many, if we combine these 2 particular values, how many values in total are we going to get? So if we're combining it, it's going to be something like this, 50 and 20, 50 and 50, 50, 50, and 100. Remove this. 50 and 150. Then we'll go to the next one, right? 120 for each of them. So you have a combination of these 2 estimators. Now imagine if you add one more parameter, right? So let's assume you add more third param, and you have, let's say, 4 values. Let's say you have 1, 2, 3, 4. What are you going to have here? Like if you combine these 3 here, you are going to have 4 times 4 times 4, which is 64. So you're going to have 64 hyperparameters combination. So what this 64 means is that you are going to train 64 different models. So if you use GridSearch, right, you are going to train 64 different models. And after you finish training all the 64 different models, GridSearch will now tell you the combination of hyperparameter that gives you the best performance. That is what hyperparameter training is. So GridSearch makes it easy for us. But you notice that training 64 model is a lot. It's a lot, especially when your data set is large. And remember that for each model would have k-fold validation done. So now, for each model, you are going to have 5 different models, right? So for each model, you are going to have 5 different models. So you are going to be having 64 times 5, which is 320 models in total. So you can now see how it is increasing exponentially. So this is basically how you tune your hyperparameters. So now imagine you now have 4 hyperparameters. You can now see the values will increase exponentially. So there's something you'll notice when you are training, and it happened during the last cohort and the previous cohort. Some of my students were complaining of the length of the model training. Some of them left their model to train, and it trained for 2 hours, more than 2 hours, some of them more than 3 hours. And if you don't really have a very fast computer, if you don't have a GPU in your system, and even if you have a CPU and it's not so fast, it will even take much longer to train, all right? So that's why I usually advise us to do your project on time, so you don't get towards the deadline and you're trying to train your data and it's taking a lot of time, and then you're under pressure and all of that. So everything you're doing, try to do it on time so you don't get yourself under pressure. So this is basically how GridSearch would work. So GridSearch has a particular problem, which is the time combination. So let me just close this one. 1, 2. So this is just this here. All right. Let's go back to hyperparameter. So now for GridSearch, you can see in this place here, this grid, we have 2 of them. So if you count, in this case, we have 5 values each, right? For n estimators, we have 5 n estimator values. So we have 1, 2, 3, 4, 5. For mass depth, we have 5. So we combine the 2 of them. So each point here is a combination of the 2. Each point corresponds to these 2 values here. All right. So you now have 1, 2, 3, 4, 5. This is going to be 5 times 5, which is 25. So you'll be creating 25 models, right, using these 2 hyperparameters. So this is GridSearch. So now this green big bubble you are seeing here corresponds to the particular model or particular hyperparameter combination that has the best results. So when you are done with your GridSearch and you get the result, then you can now select the hyperparameter values and then use it to train your model. All right. So that is basically it. So hyperparameter training is just to find the best hyperparameter combination that will give you the best model performance, and then you can now pick those values and then use it to properly train your model. Right. So that is basically it. So GridSearch goes through each of the combination. The difference between GridSearch and randomized search is that GridSearch goes through each of the combination and then it will give you the best result. But randomized search doesn't go through each of them. It just picks random combination, all right, and gives the best. So the difference between randomized search and GridSearch is that GridSearch will give you the best result. Why randomized search might not necessarily give you the best result, but it just gives you the best result out of the samples that it took from the combinations, all right? So that's why it's called randomized search. So let's just go through each of them systematically. So for GridSearch, the process here is to define a grid of hyperparameter, then train and evaluate the model for each combination, and then select the combination with the best performance. So the advantage here is that it actually searches exhaustively over the hyperparameter space. It searches through every single hyperparameter like combination. All right, so it takes more time. So the disadvantage is that it is computationally expensive and time consuming, as I've said, and it is inefficient for large hyperparameters. Just imagine you have 5 hyperparameter values, right? No, 5 hyperparameters, and for each of them you have like 6 values each. So you just know that what you are going to do, you are going to say power what 5. So it will be 6 times 6 times 6 times 6 times 6, which is 7,776 combinations. So you're going to be creating 7,776 models times 5 because of the cross validation, which is 38,000 models. So you can see how it increases exponentially. So it is computationally expensive, right? But it's inefficient for large hyperparameters. But if you have the time and if you have the resources computationally, this is the best because to give you the best combination, or you just have to trade the time and the computing resources for it. So for randomized search is a different approach. It's like an alternative to GridSearch because of its downside. So randomized search is an approach to hyperparameters where the model is evaluated for a fixed, you can see a fixed number of random combinations of hyperparameters. So there's a random selection of hyperparameter combinations, and then you now train your model on that. So the process is almost the same as GridSearch. So you define a range for each hyperparameter, randomly sample a fixed number of combinations from the range, train and evaluate the model, and then select the combination. So the only difference is that you randomly sample from the so you don't use all the combinations to train your model, you sample from it. So the advantage is that it is more efficient than GridSearch for large hyperparameter spaces, and it can find a good, you can see the keyword here is good, not best. It doesn't give you the best hyperparameter combination, just give you a good one because it's not searching through all the combinations, just searching through the randomly selected combination, right? And then the disadvantage is that it does not guarantee the best hyperparameter combination. That is the downside to randomized. So you decide on which one you want to use, all right? So we're going to look at how it is implemented. These are the differences between GridSearch and randomized search. In GridSearch, we try every combination of a preset list of values of hyperparameters and choose the best combination based on the cross-validation score. And then the random search tries random combinations of range of value. We have to define a number of iterations. It is good at testing a wide range of value, and normally it chooses a very good combination very fast. But the problem is that it doesn't guarantee to give the best hyperparameter combination, but it gives you a good combination, but not the best. All right. So GridSearch gives you the best combination, but it will take a lot of time. So just keep that at the back of your mind. It will inform your choice, right, when you are doing your project or whatever it is you're doing. Just we can implement it in sklearn. All right. So we're going to be using a data set here. We're going to try to use a data set. We'll use load iris. So let me just come here. So you import your libraries. Import libraries. So first of all, we want to use random forest. Let's use random forest. So I'll say from sklearn. You can use any model of your choice, right? From sklearn. And remember, I even forgot, when you are using random forest, it's even much worse because it's an ensemble technique. So if you choose n estimator equals to 10, that means for each, it's even much worse. That means you are training 10 decision trees. Anyways, let's not go there because the number will be mind-blowing. So I hope you got what I was trying to explain. So from sklearn.ensemble, let's use the decision tree. So we don't like import decision tree classifier. So to import, okay. So
we want to import our grid search from sklearn.model selection. Import grid. So this is a grid search CV. So this is how you import it. Grid search CV, and we'll also import randomized search CV. I hope I've not made any mistakes so far. So we'll also import data set from sklearn or data set. Which one are we using here? Let's use Iris. Let's use Iris to import. We're not really doing an exhaustive model building here, just to demonstrate research for you. Import Iris, load Iris, right? Load Iris. So we're going to import all of that, and then we come and load data. So data is going to be equal to load Iris. All right. So now there's something that I wanted to show us earlier on. There's this particular, I don't know if it's here. All right, so there's this particular parameter that you can include when loading your data set from sklearn, which is as frame equals to true. So by default, as frame is false. So what this does is that it converts this data to a pandas data frame. So if you check it now, you're going to see that this is in a pandas data frame format. So let's see. Let's data. You can see now that it is in a pandas data frame format. All right, so it's easier to interact with. So if you don't include this as frame, is by default is going to be false. So you're going to have something like this. It's going to be in your normal array, numpy array. But if you come here and say as frame equal to true, then you're going to have this, right? So I can just come here and say x equals to this and y equals to data.target. All right, so then we'll split our data, So I'll come and say x train y train, no, s train x test, y train y test. Be careful when doing this thing so you don't mix it up. You don't put s train first and s test. So s test first and s train second, or s train and then you put y train. No, you make sure that you put it in this way. Remember that you are splitting. In this case, when you come and say train test splits, if you put x here, you are splitting. Normally, train test splits just one array. So if I have just x, then it's going to return 2 split for me, right? So that's why I have x test x train s test. But if I come here and I put y, then I'm going to have 4. I have y train and then y test. So if I put another array here, like c, I'm going to come here and put, say, c this. So just to show you the arrangement of this, because this can land you in an error and you'll be confused on where the error is coming from. So in this case, you just come and say test size equals 0.2, so use 20%, and then random states size 0.2 random state. Let's just use 42. All right, so this is it for our split. Now let's move on to our cross validation. So using hyperparameter tuning, hyperparameter
Parameter. Am I too fast? Am I too fast? Should I slow down, or should I maintain the pace, or should I increase the pace? All right. So now the first thing you're going to do is that you're going to define what we call parameter grid. All right. We're going to define params grid. So, fire down as in, should I slow down or what? All right. Okay, that's great. So we're going to be using, we're going to first of all create a param grid. This is what we're going to pass into our GridSearchCV class. All right. So we're going to have. Should I go back to random forest or use? Okay, let's use random forest, right? Let me see decision tree first. Let me import random forest as well. Up. So now you can see that this grid search has CV at the back, GridSearchCV and RandomizedSearchCV. This CV means what? Exactly. So that's why I needed to explain cross-validation to you so you understand. The CV there means cross-validation. So when you want to perform hyperparameter tuning using GridSearch or RandomizedSearch, the first thing you do is to define your parameter grid, all right? So you usually call it params grid or whatever it is you want to call it, params grid. So your params grid is a dictionary, right? A dictionary always have a key value per value, right, in the dictionary. So the values you are going to have here are the parameters of the model you want to create. So let's say you want to use random forest. So you come here and just initialize. Let's just say forest. I will come and say random forest. Did I run this? I'm not sure if I ran secure. So random forest classifier. Now you're going to check for the different parameters. So you can go to this particular tab or menu to look at the exact parameter name, because that is what you're going to put in as the key in this param grid. So in this case, we have n estimators, right? We're going to bring it out. N estimators, we'll put it here. Put it in a string. So each parameter would have a list of values, because that is basically the point of this whole thing. You want to compare different values. So we're going to start from 20, go to 30 and 40. Because of time, I'm not going to use a lot of values, right? Now let me even see pre, so we don't waste much time. Decision tree classifier. All right. So for decision tree, we're going to get minimum leave split 2, criterion, Guinea, and all of that. So how many criterion do we have? We have Guinea, we have entropy. All right. So there are some of these parameters that the combination doesn't work. So there are some of these things that you'll find out later on, because when you try it, it'll tell you that this particular parameter value require this other parameter value to work. So it's something that you would have to learn, like as you practice. You learn how to like select the, but just anyone you at the first, for your first start, just select any parameter basically. So from there you will now start like moving on. So but let's use random forest first. I'm just looking at the time it will take. So we also have an estimators, then what again? We have max depth. So we're going to get max depth, right? We're going to have let's start with what do we have here? So, okay, we'll start with none and then 10, 20, 30. All right. So we'll start with none and then 10, 20, 30. So we have the last one that we have here is minimum sample split. So you can read up the sample. Make sure it's the exact name of that parameter, minimum sample. That's what came here that time to check it. I came here to check. So you have to make sure it's the same name, minimum sample split. So you can just come here, just do this. All right. Let me reduce it first because of time. Let me just reduce it because it will take a while. So I'm going to just put 2 and 5 here. 2 and 5, all right? I'll just make it 2. So this is our params grid. We've defined our params grid. So the next thing now is to like define our grid, set up our GridSearchCV. So your GridSearchCV is the same class that you'd like that you've always been working with. So you'd have parameters like different parameters that you'd have to like specify in this place. So we have estimator, we have param grid. So these are the 2 most common parameters. These are the 2 we are going to be working with. So just come here and say setting up, defining grid search. All right. So I'll come and just say grid search, and then I'll have it as GridSearchCV. So we have our estimator. Estimator here is our model. So we define our model here. We want to use our forest model. Come here and just put forest. We define it already. All right. Then we have the other. Let's just check out grid search. We have estimator and we have param grid. So we're going to use these 2 for now. So we say params grid. So params grid is what? Params grid. All right. So this params grid is this what we've defined here already. We're going to pass it into this place. So we have CV as well. But because of time, we'll not put it. So CV by default is what? None. So this is cross-validation. So if you not set it in, it's just going to not perform cross-validation. So if you scroll down to cross-validation, you're going to see that cross-validation generator, it's blah, blah, blah. It determines the cross-validation splitting strategy and all of that. So none actually none uses the default 5-fold cross-validation. So if you leave it at none, if you don't define anything, it's going to use 5-fold. Because I told you that inherently, grid search uses cross-validation, whether you specify it or not. But if you want to increase the fold to 10 or to 15, or let's say to 3, or whatever, you can now set it yourself. So but for now, let's just leave it at this, all right? So once you set your grid search and all of that, you can run it, and the next thing to do is now to train all the models using your grid search. So I'll come here and say grid search dot fit, and then I'll now train it on my S train and Y train. I hope this doesn't take a lot of time. So once I do this, it's going to actually now start training it's now going to do all the things we've explained. You're going to go through all the combinations and all of that. But we actually did it very fast. So you can see that it did it very fast. So we've gotten our grid search. So let's see if we can even add more parameters here. 50, that's a 9, 15, 20. say 7, 10. So you see that it will take you a lot more time, like take more time now because we've added more parameters. All right. So when you're doing yours, it might take more time depending on the number of parameters you have. All right. So you can see, and this increases exponentially. Once you add, let's say, one more value to each of them, it doesn't just increase by 2 or plus 2, it increases exponentially. So if you took, let's say, 1 minute the first time, if you add more values, it can take you now 5 minutes. If you add more value, it can take you like 20 minutes, right? So it increases exponentially. So you should be careful of how much like parameter, although you can, if you have enough time, you can actually try it. But you can see that this one is now taking more time than the initial one that we had because we added more parameters here. So it's done already. That's fine. So we now have our grid search classifier completed, right? So we're going to just go ahead and check, because what we want to get from the grid search is the hyperparameter combination. So we're not using this thing to make any prediction. We just want to get the combination of hyperparameter that give us the best result. So to do that, you use this particular method on your grid search object. So .best params, all right, with underscore. So it will now show you the combination of parameter that give you the best score. So you can see now that we had max depth equals to none, minimum split equals to 5, and NS equals to depth. So these are the parameter, or this is the combination basically that gave us the best model. So I think let me come. I want to be sure that let me see, print of the name of the, I want to be sure of the method name. All right. I think it's best result or something like that. So we have it here. Best score. Okay, it's best score. So you can see it here. You can see best estimator or whatever. So just come and say best score. Copy it. So you can see that this is the score that we got, right? You can see that this is the best score out of all the models that we got. And these are the parameter combination that give us the best score. So you can see how easy it is to use grid search for hyperparameter tuning. So this is basically what hyperparameter tuning is. And grid search makes it very easy. All right, so randomized search is almost the same process, right? So from a randomized search, you import randomized search as we've done. You do your normal splitting and all of that. You define your param grid. And for randomized search, you actually include something which is your random states and n eta. So these are the things that you introduce in random search. You introduce n eta and random. So let's just quickly do it. So define randomized search. So come here and say random search. And I can just say randomized search CV. All right, so of course you have your estimator, which is going to be forest. You have params grid, which is going to be okay for randomized search. It's called param distribution actually, not param grid. So you just put your params grid there. It's a params grid. All right, and then you indicate n eta. So this n eta basically means how many samples do you want? How many like iteration of because it does sampling. So how many times do you want it to sample, right? So you can just say, let's say 100. Let's just confirm what that means here.
So then just so n eta. So n eta is the number of parameter settings that are sampled. All right. So this is the number of parameter combination that are sampled. So I feel, anyways, let's just see, because 100 might be more than the combination that we have here. So 4 times 4 times 4, that should be about 64, right? So let's just try 100 first. Let's see what it's going to give us. So random state, remember what random state does. Anything that involves sampling or random selection, you can use random state to fix that particular state, all right? So we get random search, and then we can now fit it here. So random search dot fit x train y train. You see now, you see what I was talking about. Now, this iteration here is 100, but it is more than the number of parameters that we want to search through. So it will give us an error, basically telling us that the total space of parameter is 64, which is smaller than the n eta. So your n eta has to be less than the parameter space. So this GridSearch, where this params grid we are having is actually a small params grid, right? Ideally, you're going to test on a bigger range of hyperparameters, right? So you would most likely need to specify more than 100 in randomized search. If you are using this kind of parameter grid, you just use GridSearch because it's going to be fast. You don't have a whole lot of combination. So in this case, we're just going to, let's say, add more. Yeah, we add 5, 5, 5. You see that it will now be 125, right? Let me just add 100 here, and add 30 here, and then add 20. All right, I'll run this, and then I'll come here and run this. So it's just going to sample through 100 of the parameters combination that we have, right? So obviously it's going to take more time because it's higher than 64 that we did before. Remember that GridSearch used 64. It took that kind of time, and this one is 100, so it's going to take more time. So if n eta equals to the number of hyperparameter, what do you think we are doing at that point? Can someone just tell us, what do you think we are doing when n etas equal the number of hyperparameter combinations? There's no point, let me just answer, there's no point using randomized search in that case because we are literally doing grid search, right? So we are literally searching through all the combinations when n eta equal number of hyperparameter combination. So the reason why you're using randomized search is because you don't have the time to go through all the combinations. So you just want to like sample a particular combinations and then select the best out of that sampled one. But if you think the parameter combinations are not so much, you can just go ahead and use GridSearch. So GridSearch is always the best unless you have a whole lot of combinations, all right? Like the combination is, you have the parameter combination is a whole lot. Then you can now go ahead to use randomized search. If not, you use GridSearch. You can see how long it is taking now, and this is just for 100 iterations. Now, just imagine you are working on even more hyperparameters. So maybe you add 2 more hyperparameters here, and so it's going to take a whole lot of time. So you can see the time consumption I was talking about, and this is just for randomized search. So it is done already, and you can see the whole thing here. It's random forest. So you can now come here and say random search dot best params. You can see that these are the out of the 100 sampled parameters. These are the combinations, or this is the combination basically that gave us the best score. Right, I hope like this makes a whole lot of sense because doing it manually is very, very tasking. So best score
So the best score is 95.8. For this one, so it's almost the same thing, right? So it's almost the same score. So you can see now, you can now go ahead and train your model. You just come here and say, just copy your forest stuff here. Come here and say random forest classifier n estimator equals to 50, minimum sample split equals to what? 10, max depth equals to none, right? You can include more. You can even include criterion. Criterion is, you can use Gini or entropy. So you can even come here and add criterion in the param grid here. You can say criterion. Okay, not here. Should be in the params grid. Yeah. We are done already. We are done. So we are ending class now. So you can make it Gini or entropy. All right. So these are the, so it will now add this combination to everything, and then you will get the combination. So this is how you perform hyperparameter tuning using. In case you now train your model this particular combination of hyperparameter, get your evaluate it and everything, and go. So that's basically it for hyperparameter tuning. So in understanding overfitting, underfitting, bias and variance is crucial for building effective machine learning models. Hyperparameter tuning like GridSearch, RandomizedSearch helps in optimizing model performance and balancing this aspect to ensure that your model generalizes well to meet data, leading to better prediction. So what you're trying to do here is just to get a good model, right? Basically. So I believe this class has done justice to explaining what overfitting is, underfitting, and how to perform hyperparameter tuning. So you have to do your own research as well to understanding the different hyperparameters, right? I've showed you how to see them and how to read the documentation. So you can just pick it up from there and just move on. So it's your own discretion to determine how many hyperparameters you want to use, right? So I won't be the one to tell you that. All right. So with that, we've come to the end of the class, and I'm going to be taking a few questions as usual, and then we call it a day. So we have Perry. Perry, this is your first time speaking in class, right? That is nice to see. So please ask your question, Perry. Raise your hand. All right. Edith Young Moses, ask your question, please. Hello.
Evening.
Good evening.
Hello.
Yeah,
Evening, please. I just want to ask in terms of the. Hello.
I can hear you. Go ahead, please.
Hello.
I can hear you, Moses.
Okay. In terms of choosing the what we are going to use in training our data set, let's say I want to train it with let's say like the random forest, the decision tree. Should I run the parameter first, so that I can be able to choose it, or should I just stick to one particular one? So I'm just confusing that parameters.
The essence of the hyperparameter is to get the parameter combination that will give you the best value. So let's say you just choose random parameter values. You're not sure if that's the best hyperparameter to use. All right. So you don't really know if that's the best combination. So you might be missing a better performance just because you've not selected the best hyperparameter. So this particular process helps you pick the best hyperparameter that will give you the best performance. Do you understand?
Yes. Okay. Thank you. So, what I want to confirm again is it also based on using different one? Let's say if I'm using the decision tree, can I use something similar and use some other thing for the other ones too? Or is it just based on only one place?
I really don't know if I get a question, but when you are setting your hyperparameter tuning, you set your parameter grid based on the algorithm you are using. If you use random forest, you set a different parameter grid. If you are using logistic regression, you set a different parameter grid because they don't have the same hyperparameters. You understand? If you are using decision trees, you set a different parameter grid because they don't have the same hyperparameter. So you do this tuning separately for each model you want to create. So if you want to use 5 algorithms, right, you do this process 5 different times because they don't have the same hyperparameter grid. So the only thing that might change is the parameter grid. You can just set different for different models and then use your grid search or your randomized search to search for the best combination. Do you understand?
Okay, thank you.
All right.
Thank
if you have any further question, you can ask. If you need more clarity, you can just ask on the Q&A. Probably if it's something that you need, like even more clarity on. I don't know if I'll, but just drop it on the Q&A group and tag me if you need more clarity. So, Hioma, please ask a question. Hello. Yeah, good evening.
Okay.
Yeah, I can hear you.
In a situation where your model is overfitted, like you're having overfitting due to maybe, let me say, too much of training time, what can someone do about that?
I've already showed us how to deal with overfitting, right? And you can, depending on the algorithm you're using, you can actually terminate or stop your training when it reaches a particular criteria. All right. So you don't allow it to train to the end. I don't know if all algorithm has n eta, but logistic regression, as we saw, has n iteration, right? So n eta is a parameter that would let it train for this number of iterations, all right? So you can reduce that parameter so you don't train as much as like you trained it, right? So it doesn't overfit. Or you can, for decision tree, there are parameters like max depth. So max depth is a criteria to stop training when your tree reaches a particular depth. All right. So there are some things to do to like terminate training. So these are still part of the hyperparameters that we are talking about. So these things are still hyperparameters. They are values that you can like tweak to like just coordinate the training and just help you with the performance.
Okay, sir.
Do you understand?
Yes, sir. I do.
Did you get what I just explained?
Yes, I do. I understand.
All right. Okay, Chin, your hand is up. It's a Chima. Please ask your question. You raise your hand, so please ask your question, please. All right. So I think at this point, okay, Abdulhamid, your hand is up. Ask your question.
Good evening, sir. Can you hear me, sir?
Oh yeah, I can hear
sir.
you now.
Good evening.
Yeah.
Can you hear me?
Okay. I can hear you.
My question is on clarification on the bias and the variance. So please, I want to understand: is it when the variance is less than 20 is when it's low, or is it when it's less than 10? So that's what I want to understand.
Anyways, the thing is that the recording will be made available. So I think I kind of touched on that, and probably you didn't get it then. So, but basically, there is no fixed point for determining variance. There's no like hard-coded number or value. But the rule of thumb is just when the difference between your training set and your test set accuracy or performance is between 5 to 10, then the variance is normal. It isn't high. But when it is greater than 15, let's say between 15 and 20, then you can consider the variance to be high. All right. So it's just in general. I think you just follow this rule basically. So when it is within this range, you can now know whether the variance is high or not. So the bias, obviously, you know it from your training accuracy. When the difference is, let's say, greater than 15. So let's say if you're having, let's just say starting from 70, if you're having 70% accuracy on your training, it's not really a good performance or metric. So you should know that, this is having high bias already. And then if your test set is having even 50%, then you know that it is having high variance, and then it's actually underfitting. So these are the things you check to help you know which one is overfitting. Just take your time to study these things. Take your time to go through the video and just and understand it. Right? It's actually something that might not come easily at the first time, but with time you get to understand it perfectly. So yeah, I think that is going to be it. Well, I hope that answers your question.
Okay, thank you. Yes, sir. Thank you very much.
All right. So you're welcome. So we're going to be closing the curtain at this point. Let me just share my screen. So thank you very much, everyone, for your time. Yeah, Nigeria, good evening.
Thank you so much for today's class. Sorry for interrupting. Someone just reminded us on the chat. He said we're going to do ROC cuff.
Oh yeah. So we actually I'm planning on having a class within the week again this week. So we are going to have to shift it then. So by at least we've gotten to understand a lot of stuff. So when we are comparing across models, it's easier for us to understand it. So don't worry, we are still going to do it. It's going to be in our next class. I don't know what date particularly. Either it's going to be on Thursday or Friday. So we'll have that class either of those days, and then we have our last class on Saturday next week. All right. So yeah, thank you for the reminder, and thanks to the person that brought it up. So that's going to be it. Please do well to go through the videos that we've been putting out there. It's the reason why we are doing that is just for your own benefit, so you can go through it over again and understand some concepts that might have eluded you during the live class. So I really believe that you all are getting a lot of value from this, and you are being transformed into a capable data scientist. So at this point, you can literally call yourself data scientist, even if you came into this program with no knowledge at all. You're a data scientist. So at some point, some opportunities that might come up, I might come here to maybe pick some of you to do some things. So you are literally a data scientist. So just live up to it. Try to continue with whatever it is you are doing to get better and all of that. So I'm really, really proud of everyone here. Trust me, it is not easy, especially data science. I know someone that wanted to join this program. The person wanted to I know. She wanted to do. She was asking for a particular track. I gave her options. I said she would go for project management. And I'm not trying to compare anything, but in terms of complexity and technicality, project management is at the bottom basically. It is one of the easiest to entering into tech. So the person was the project management course is overwhelming, that they don't understand anything, and they literally, the person dropped out. So I'm basically just saying this because most of us have stayed here from day one till now, despite the challenges, these technicalities, the complexity, everything basically, and you are still here now, and you've not given up. That's actually a good attribute, right? It's a good attribute. Show that you have resilience, like you have the mental capacity to do difficult things, right? So trust me, if you can get here, there's nothing else that you cannot do. Like there's really nothing else I can. If you can finish with what we are doing, if you can finish your project, do everything, there is really, unless you just choose yourself to just slack and just sit down and be lazy. But if you really put your mind to it, for the fact that you are here, there's really no height that you can attain. It's just, the only thing it's just going to take is time. All right, it's just going to take time, and like just time basically, and you would get to see opportunities that will basically just change your life or whatever. So that's going to be it for today. I'm hoping to see you all in the next class, which is going to be communicated later on today. What, Williams? What did you just say? Confused data science. People just crack me up here. Anyways, don't worry. Your confusion will soon be clear. You'll soon gain clarity with time. Okay, so thank you very much for your time. Please do drop what you learned in this class and enjoy the rest of your day. And please do have a splendid and a beautiful week ahead, and enjoy the holidays too. Thank you very much, and good night.